Hi, I'm Philippe Wouters. I've used Portfolio123 for years as a systematic investor, and today I'm trading live machine learning models built with AI Factor. AI Factor is a no-code machine learning tool that lets you build linear and nonlinear models to uncover hidden return patterns. I created this video to explain the key settings behind building and backtesting a machine learning strategy. To keep it AI native, I'll let an AI voice take it from here.
Let's build a custom AI factor in 20 minutes. We're aiming for relative strength within the broader market. First, we set our target to MREL. This tells the AI to optimize for stocks with the strongest 3-month relative performance. Next, we'll set our training universe to the Russell 3000. This gives our model a massive data set across large, mid, and small-cap stocks. We select the IWV benchmark. We'll name this 1R3003M rank for easy reference in our strategies. Hit Create, and our AI factor is ready to be set up. Next, we confirm the target and universe. The most important decision here is target normalization. This determines how the AI scales your 3-month relative return. Choose Dataset if you're using Z-score scaling. This uses global statistics, like the mean and standard deviation of the entire history, to scale your target. Alternatively, selecting Date treats every time period as an independent group. It's perfect for both Z-score and rank scaling, ensuring the AI focuses on the winners of each specific day. We are going to pick Date. Next, we are selecting Normalization. Scaling is essential for AI performance. While Z-score is a classic statistical approach, financial data is notoriously messy, which is why we have two critical safety valves. First is the trim percent. We allow a trim on each side of the feature distribution, which is by default set to 7.5%, and omits 15% of the data in total. This ensures our mean and standard deviation aren't skewed by temporary market anomalies or data errors. Next, we set an outlier limit. By clamping Z-scores at 2.5 standard deviations, we prevent extreme outliers from over-influencing the AI's learning process. However, for our R3000 factor, we're selecting rank. Why? Because rank provides the company's position relative to its peers, while Z-score provides the raw distance from the average. Rank provides a uniform distribution from -1 to 1. Now we're focusing on the period settings, where we define the when and how often of our data. First, let's look at the time frame. For this model, we are going back 20 years, starting in November 2005. Why 2005? Because many powerful stock factors require a deep look back. By starting here, we ensure there is enough historical data for 5 or 10-year factors to calculate properly. We will be adding an EPS 5-year growth factor and want to ensure we keep the number of non-available data points low. Next is frequency. This determines how often the AI samples the market. We're selecting every 4 weeks for this run. Keep in mind, this is flexible. Depending on your strategy, you can go as granular as every week or as broad as every 13 weeks. Now let's talk about a critical safety setting: max return. Individual stock returns are capped by this limit. This is vital if you are working with universes that include low liquidity stocks or penny stocks, where a single outlier, like a 1,000% jump, can skew your entire report. 2 things to remember. First, this limit does not impact the actual features or targets in your dataset. It only affects the validation reporting. Second, you may need to adjust this value based on your frequency. A 200% cap might be reasonable for a 4-week look-ahead, but it might be far too low for a 13-week frequency. We can now add our features. There are 3 ways to add features. You can add factors from our predefined factor base, you can add custom formulas, or you can import from an existing system. First, click the Add Predefined button to access our library of vetted financial metrics. To capture how a stock is performing against the broader market, navigate to the Technical folder, then select Relative and click on Relative to Benchmark. When clicking on a specific feature, you can see the full formula, which shows exactly how the metric is calculated. You can also view the distribution of values. This visual breakdown helps you understand the spread of your data across the universe, allowing you to identify outliers. We will now select all 5 available timeframes. Check the box to keep window open to add them one by one. Now let's add a custom feature and go over all the options. Click Add Formula, and we'll provide the name and formula. We'll add earnings per share 5-year annualized growth. First, we select the formula type. This tells the system how to handle your logic and filters which normalizations are available. There are two main types. Ratio, for formulas that evaluate to a single value, like ours. Series, for formulas using a loop function that iterates in increments. Next, a two-step normalization process. Step 1 is longitudinal. This compares the stock to itself over time. For our formula, we'll leave this as skip to pass the raw value directly. Step 2 is cross-sectional. Date compares the stock to the market. By selecting date and subsector, we normalize the value against its peers, telling the AI if this 5-year growth is high or low relative to other companies in the same industry today. Once configured, click Add to include it in your dataset. We will add all 3 options, as we want to see which version will work best. You can see here the 3 custom formulas we just added. To leverage work you've already done, click the Import button and select Ranking System. This allows you to bring in the factors from any of your saved rankings or our library of proven models. From the Selection menu, we will choose the Core Combination Ranking System and add all 64 factors to the AI features. This is a powerful shortcut to leverage your existing ranking expertise. Now that we have defined our features, it's time to generate the data for our AI to analyze. Navigate to the Load tab. Here, you'll see a summary of your configuration, including the date range, your chosen universe, and the total number of features we've added. To begin the process, click the Load Dataset button. Before starting, you'll see an option for Target Information Regression Sample %. This is a powerful tool for analyzing how well your features predict the target, but it can be computationally expensive. For this run, we will go for 100%. The system will now go through 2 decades of market history to calculate every factor and apply the 2-step normalization. You won't be able to change your settings once the load begins, but you can start setting up the next step while the data processes in the background. The Feature Stats page helps you audit your inputs before training. The Target Information Regression bars show the statistical dependency between each feature and your target. Longer bars indicate a higher predictive potential. This metric, based on mutual information, captures both linear and complex nonlinear relationships. Also review the NA percentages to ensure your best features have enough reliable data coverage. Let's move to the Validation tab to set up our test. Let's break down the key settings, starting with the gap. The gap is the number of weeks between the end of your green training period and the start of your orange holdout period. By adding this buffer, you reduce the risk of, quote, data leakage. We'll keep this at 52 weeks. We have 4 validation settings. Basic holdout is the most straightforward validation method. It simply splits your data into 2 distinct parts. 1 single training set to build the model, and 1 validation set to test it. The holdout period defines how much data is set aside for that validation. On the chart below, this is represented by the orange bar. It is crucial to remember. Your final results and performance metrics are based entirely on this orange section. Because this is the proof of your model's effectiveness, the orange part needs to be long enough to be statistically meaningful, usually covering different market cycles. Let's set this to 72 months. This period is the real-world test. Because it covers various regimes, your results here tell you if your model is robust. Finally, the testing toggle adds an extra layer of rigor by setting aside a final out-of-sample dataset that provides a completely unbiased estimate of real-world performance. Notice the dark green bar on the chart. This is the training data for this final check. But the real final exam is the red bar at the end. This is data the model never saw during training or validation, making it a completely blind test. By running the models again to see the results of this red period, you verify that your 72-month orange performance wasn't just over-optimized, but a sign of a truly robust strategy. Basic holdout is a great starting point. Time Series CV uses an expanding window to simulate walking through history. Look at the green bars. Fold 1 starts with years the first 8 years. Each fold adds more time. Fold 2 trains on years 1 to 10 to predict year 11. With 4 folds and a 24-month holdout each, you aren't just getting 1 result. You get 8 years of cumulative out-of-sample testing to review. This allows to review the model's consistency across multiple market cycles. If you want to focus on how your strategy performs using only the most recent data, rolling time series cross-validation is your best choice. Unlike an expanding window, the rolling method keeps the training period fixed. For example, always exactly 5 years. As we move through the folds, the window slides forward. With 4 folds and a 33-month holdout each, you get 11 years of total results. It's the ultimate test of how your model adapts to the now across different eras. Our last method is K-fold CV, blocked. We divide the entire dataset into K equally sized blocks. Unlike standard K-fold, which shuffles data, blocked K-fold keeps time periods intact. With 4 folds selected, the 20-year dataset is partitioned so that you get 4 distinct holdouts for your model. As our final selection, we will go with basic holdout, as it is a simple approach and similar to classic ranking. We put the validation holdout to 72 months. Now we'll add our models and choose our algorithms. We have several powerful options to choose from depending on your data and goals. Deep Tables is a specialized neural network for tabular data that automates feature engineering and hyperparameter tuning to find complex, nonlinear relationships in your factors. We are going to select Keep Window Open and click All and Add. Next, we have ElasticNet, a robust linear model that combines the strengths of both lasso and ridge regression to handle highly correlated factors while automatically filtering out the less important ones. You can click Show on any model to reveal its specific hyperparameter configurations and descriptions. In this list, you'll see 2 main types: bidirectional models, which allow factor weights to be either positive or negative, and directional models, which restrict weights to be non-negative so that signals only contribute positively to your expected returns. Now, let's add our other 3 linear options: lasso, linear regression, and ridge, all of which align with the latest scikit-learn standards. Lasso is ideal for simplifying your strategy, as it uses regularization to shrink the coefficients of weaker factors all the way to 0, effectively performing automatic factor selection. Linear regression is our most straightforward parametric model, fitting a direct linear relationship between your factors and target returns without additional regularization. Finally, ridge regression is great for handling multicollinearity by penalizing large coefficients, ensuring that no single factor has an outsized or unstable influence on your model. Extra trees is an ensemble model that introduces extra randomness when splitting data, making it faster to train and more robust against overfitting than a standard random forest. Generalized additive models offer a flexible middle ground, allowing you to model complex nonlinear relationships between factors without losing the interpretability of a linear model. Keras neural network uses layers of interconnected neurons to capture complex, nonlinear signals in your data that simpler models might miss. LightGBM is a highly efficient gradient boosting framework designed for speed and low memory usage, making it ideal for handling large-scale datasets with high accuracy. Random Forest builds a forest of decision trees and averages their results, providing a robust, non-parametric approach that excels at capturing complex interactions without relying on data distribution assumptions. Support vector machines are effective for finding the best boundaries between data points. XGBoost, or extreme gradient boosting, is a powerful sequential learner that builds a strong predictor by iteratively correcting the errors of previous weak models. Instead of testing AI models one by one, the grid function lets you mass create and backtest dozens of hyperparameter variations all at once. Click Add Grid and view the Combinations column to see how many model variations will be deployed. Select a predefined setup like this lasso regression grid and check your total combinations. Once added, you can track the newly generated variations directly in your model overview, where you can monitor their specific hyperparameter settings, like the alpha values for these lasso regressions. Now that our setup is complete, it's time to launch the models. First, we'll select the master checkbox at the top to highlight 100 models at once. Next, click Validate to kick off the validation phase. We click No to save validation prediction. On this configuration screen, you can see the cost breakdown per hour for each CPU and GPU model before we hit Start. We'll let the validation run and come back later to trigger the final test runs. The faster models process in just a few seconds, while the more complex ones will continue to run in the background. We can now go to the Results tab, where you can rank your models using data science metrics or portfolio performance metrics. Click Rank Columns Edit and toggle the metrics you want to view and rank. We select Spearman for raw predictive accuracy, along with high minus low AVG% and high AVG% to instantly rank our models by their actual top quantile performance and spread. Since we are running a Russell 3000 universe, we'll set our quantiles to 20. This breaks the data into 5% buckets of about 150 stocks each, which gives us excellent statistical significance while eliminating individual stock noise. For slippage, we'll set it to 0.25% to act as a realistic baseline for the smaller names in the index. When evaluating our models, the lift chart is where we see how well our predictions translate into real-world performance. The blue line represents our predicted bucket rankings, from lowest to highest. The orange line shows the actual subsequent performance. Notice how closely the actual returns track our predictions as we move up the rank. With a 0.095 Spearman correlation, the upward trajectory confirms strong predictive power. On the Portfolio tab, we can evaluate our model's performance over the 6-year validation period. The dark blue line tracks the top bucket, orange shows the lowest ranked stocks, and black is our benchmark. Toggling on the high minus low spread reveals in light blue the pure, compounded alpha. Notice how it preserved capital through the 2020 COVID dip and continued to climb as the market normalized post-COVID liquidity boost. Below, the period return bars break this down annually, showing year-by-year performance against the benchmark. We can also toggle on the high minus low spread to see the year-by-year performance. Transitioning over to the Return tab, we can break down our performance by specific quantiles. Looking at the annualized returns, the blue bars track our top long choices, the orange highlights our shorts, and the black dashed line marks our benchmark. This clear, step-like progression from bucket 1 to bucket 20 delivers in a strong Spearman correlation of 0.92, proving the model's outstanding ranking accuracy. Now that we've narrowed down our top performers on validation data, the critical next step is to run a true, out-of-sample test on our top models. By testing them on completely unseen data, we can see which strategy truly holds up and avoids overfitting to the historical period. To do this, we'll head back to Validation, click Models, type the name of the model to test in the search bar, and click Start Testing to see if the model holds up during this unseen period. Heading back to the results page, we can instantly view our out-of-sample performance by checking the testing box. When going to the Lift tab, notice the capital T next to the model names. This indicates our completed test results are ready. Now we can toggle directly between validation and testing to see exactly how well our strategy holds up on unseen data. And as you can see, the lift chart holds up nicely. Now that our test results have confirmed the alpha is real, we move to the final phase, creating our actual AI predictors. We click Add Predictor, select our winning Light GBM Medium 2 model, and we are actually going to build 2 versions. First, we'll create a historical predictor by setting the training end date to 5 years ago, back in 2021. This gives us a 5 years of out-of-sample window to backtest its performance inside the stock screener. Second, we'll repeat the process, but this time we'll hit max to train the model on the full historical dataset right up to 2025. With both predictors set up, we have one perfectly primed for screening tests and another fully updated for live market deployment. By clicking the FX icon, we reveal the predictor formula and a quick link to the stock screener. From here, we can instantly run a screen to see how the model's top-ranked decile actually performs. If we look at the Quick Rank section, the model has automatically plugged in our custom AI factor formula. Next, we configure our backtest screen settings to match our backtesting strategy. We'll adjust the backtest period to cover exactly 4 years, from December 2021 to December 2025. Finally, we'll cap the maximum number of holdings at 150 stocks, which is similar as our 20 deciles results. We then click Backtest. The backtest graph shows exactly how the top 150 stocks picked by our 2021 predictor would have performed, delivering a solid 39.6% total return across a completely clean, 4-year out-of-sample window. Next, let's look under the hood by navigating to the Importance tab to see exactly what driving factors our model relies on. Because Light GBM is a nonlinear, tree-based model, it doesn't just look at variables in isolation like a traditional linear regression would. Instead, these coefficients represent a feature's total contribution to splitting data across the decision trees. We now move over to the Predict subtab to see what the model is recommending for live trading right now. From the drop-down, we'll select our production-ready maximum length predictor, the 2025 model. We hit Predict, and the AI instantly generates our fresh, top-ranked stock recommendations for the current market. And that's how you build a powerful AI factor from scratch. But if you want to skip the build time, we've done the heavy lifting for you. Our AI developer, Andreas Himmelreich, has officially launched 2 brand new, fully optimized AI factors tailored for the S&P 500 and S&P 1500 markets. Powered by a massive dataset of 163 fine-tuned features, both models are live right now. Dive in today for complete, transparent access to all the underlying predictors and results. And we aren't just stopping there. We have officially made these AI factors available to you as a live strategy. Click Live Strategies, and you'll notice a brand new subcategory AI factor. In the overview table, you can see exactly how this machine learning predictor is powering the ranking system, and easily compare its performance side by side with our other core models. Let's dive into the AI factor S&P 500 to see the true benefits of machine learning in action. In a competitive universe like the S&P 500, achieving consistent alpha using classic tools is incredibly difficult. But watch how the data speaks for itself. First, look at the Sharpe ratio coming in at an impressive 1.11. Next, check out the max drawdown. While the index dropped over 24.5%, this AI model max loss was only minus 18.89%, with an annual turnover of only 224%. These are the kinds of results that are harder to accomplish with traditional linear tools. Now it is your turn to put AI Factor to work. Start by exploring our new AI Factor S&P 500 and S&P 1500 models to see how machine learning can be used in live strategies. Then build your own AI factor using your own investment ideas, universes, targets, and factors. Use the predictor where it matters, in screens, ranking systems, simulations, and live strategies. Start simple, validate the results, learn from the data, and keep iterating.